Hello everybody and welcome back. So in this next lesson we're going to continue talking about noise, but we're going to dive into Vex now and see how we can get noise into Vex in exactly the same way as we have it in VOPs. As I explained before, if you just want to make basic noise and do just the basic things with it, it's probably still advisable to jump inside of a VOP because it is a lot easier, especially because there are so many parameters on the noise and different types of noise, and often you actually want to combine multiple noises, so you'll have maybe even several different types of noise that you're multiplying or adding or maybe taking a maximum between one and another, just to sort of break up the noise so it is more random. And if you're doing this, it's definitely a lot easier to do it inside of a VOP. The reason being is because the parameters are contained on the node of the noise, whereas in a wrangle there are no nodes, there are lines of code, which means when we promote all the parameters, we end up just with a lot of spare parameters, and you have 3, 4, 5 different frequencies, different offsets, different amplitudes, all linked to different noise functions within one snippet of code. It can get a bit messy. So I would recommend using VOPs for noise, and often I'll use them to create a noise and then dive inside of a wrangle and just do whatever else I want to do inside of a wrangle, because there are a lot of things that are a lot more efficient and faster to even type in a wrangle. But sometimes that's not going to be possible. Sometimes you want to, within a loop, maybe create some sort of noise and then do a comparison and then maybe apply that noise or alter the noise based on certain conditions inside of loops and blocks, and so sometimes we're going to have to do it, and that's what I'm going to show you today, just so you know exactly how, in particular because there's a few kind of hidden parameters inside of Vex when it comes to noise. So I want you to at least know this technique in case you ever need to use it. Okay, so I've got the exact same scene set up as the previous lesson, so just as a way of visualizing our noise in a sort of a grid and a cube. Okay, and if I dive inside of this VOP where I'm setting my noise, I just have a basic alligator noise on a turbulent noise function. So last time we were using the anti-alias noise, but now I'm using the turbulent noise, and it's just got the same type of parameters that we were looking at. Okay, and you can see the result. Now, it's important to note that there are different types of noises. Okay, and you can actually just even look up the different types, or I'm sure the help file for the turbulent noise will actually explain all the different types of noise and what they do. The most important thing to understand about each of these different types of noise is actually what kind of the range that it returns, because some noises like alligator are returning a 0 to 1, okay, which is very, very useful to know, because then we know we can use just a normal fit01 function or something like that without clamping or losing any values. We can just take a fit01 and then fit it to whatever range we want it to be. But something like a sparse convolution noise is going to give us a negative 1.7 to positive 1.7 when the turbulence is 0. So it's got this kind of variable range depending on our other parameters. A lot harder to fit one of these noises. Having said that, sparse convolution noise is one of my favorites. It actually produces really nice looking rough results. But yes, you do have these negative values, which sometimes you actually want. If you take the absolute of this, then it kind of creates these little mountains, because you end up with kind of sloping rises and then very sharp sudden reversals on the troughs. So you kind of end up like this nice rolling hill, and then suddenly it'll have like a sharp V and then rises up again. It's very, very cool for creating a lot of different things, and often when I'm creating noise that has to do with fluids as well, then I'll use sparse convolution. So but this is just all, you know, personal preference. I mean, you can experiment with all the different noises and see which one works for you. And in most cases, there's going to be, you know, a noise for each different, you know, each different case. Sometimes you want alligator noise. Sometimes you want, you know, your purlin or original purlin, which goes into the negative. Okay, and it does explain here. It shows you the string value, but these are actually the names of the VEX equivalents of this. Okay, so we have P noise, O noise, S noise, A, X, and we do have a whole lot of other types as well. In fact, I'll jump into the VEX section now and I'll show you. So in our normal VEX functions section, we have a subsection for noise and randomness. Okay, and here's our A noise, so our alligator noise, and then we've also got so what were the others? Purlin is there. Well, it's either P noise or noise, and there is a same as with the alligator noise. There is actually a normal version and then a periodic version as well. So you'll see a lot of them have this period. So depending on what type it is or what type it's returning, there will sometimes be only a single period, or it'll be multi-dimensional. So there'll be X, Y, Z, or sometimes there's even 4-dimensional noise with then 4 different periods. So, but period basically just causes the noise to change periodically through n-dimensional space. So depending on whatever we're casting it to, or the position vector as well. So the period here is not calculated on here. So in the VOP we're essentially using these beginning ones, and most of the time you're going to want to use this as well. Okay, so we've got our alligator noise, our purlin noise. The sparse convolution noise that I mentioned just now is just S noise. So this is the one that I often like to use, and then we also have the X noise, which is our simplex noise. Okay, and it gives a little write-up on each one, just kind of explaining, you know, what it does, what it can work with. You see here, this one actually can work with vector 4. So, you know, they're designed to work for specific purposes. So you'll want to kind of read through these and just get a sense of what you can use them for, or the different scenarios where you'll want to use them. V noise, for example, is Voronoi noise, and that is used in very specific situations. Often you want to create clusters like within your particles, or you want to actually create fractures. So your Voronoi fracturing, you know, when you're going to do rigid bodies, you know, breaking actual objects is normally done using a Voronoi or a similar, you know, functions similar to Voronoi. So, you know, this one's really good to know how to do in VEX, because you can actually then do some really cool things, iterate through loops and then fracturing objects using Voronoi. Whirly noise as well as another type of cellular noise as well, which gives you really cool results. And it's good to note that the sparse convolution noise that I like so much is actually based on a whirly noise, but it's sort of like a weighted kind of noise. So the same way that I showed you with our PC opens, where we can, with a PC filter, are grabbing values based on the weight. So in other words, the distance to the object will determine how heavy that value is weighted within the average. So sparse convolution noise does something similar, but then based on a whirly noise. So yeah, there's a whole variety of different noises here that you can use just to kind of get the look that you want. Oh yes, curl noise is another one, a good one to show you as well. So curl noise will just do, so it computes divergence-free noise based on purlin noise. Okay, so then this is how you'll normally get those like nice kind of curly vector fields when you want to, you know, just create some initial velocity for your particles or something like that. So Lots of cool different types of noise. I encourage you to experiment, play around with them. Just take an afternoon and just sit and type them all out and see what you can kind of get them to do. All right. And also don't forget, I'll just show you at this point because this is quite a cool way to do it, is just when you have found a noise that does work in PointVop, but you just want to actually include it in your Vex, then don't forget that you can right click and say view Vex code, and in here actually if you go right down to the bottom where this is being run, you'll see the different types. So here it's checking whether we've selected A noise or O noise, and then it will switch between those two, and then here it's running the correct noise and the S noise, so the sparse convolution noise. So those are all these options in here. Okay, just as a reminder of what it's doing. Okay, so what we're going to do now is I'm going to show you how to rebuild this alligator noise in Vex, just so that we can, because alligator noise just got all the same parameters and stuff, so it's nice and simple to start with. And I'll show you the hidden parameters as well. Okay, so we've got our PointVop there. I'm going to drop down a wrangle just next to it, and we're going to start typing in here. Okay, so I'm going to store my noise in a separate variable. It's often advisable to do this, and then you can cast it depending on how you want that noise to be altered, and maybe even alter it in several other lines before you apply the noise. And you always want to obviously calculate the noise only once if you can. So if you're applying it in multiple places, then you want it to be stored in a variable. Okay, so because we were creating single, sort of grayscale noise over here, is just 0 to 1 values in X, Y, and Z for the color attribute. I'm going to be casting it as a float, but I'll show you how the casting works just now as well. So we're going to just create a float variable, and I'm just going to call it noise, and then I'm going to run the A noise. Okay, now that's just because I know that A noise specifically is alligator noise, but like I said, you can go check or go through this list. Okay, and if we jump to the A noise in here, you're going to see there's a lot of different ways you can do it. I mean, here we can cast as float or vector, so that's what that tells us. It also shows us that we can do it with just the position. So the turbulence, roughness, and attenuation and this period are optional. So we could actually just stop there. We could just feed it position, and that's it. And in this case, look, remember last time we spoke about all the different ways that you can feed the position. It doesn't have to be point position. But in this case, I'm just going to stick to point position because it's the easiest to visualize and see. But use the last lesson as an indication of how you can also drive your noise with different variables and attributes. Okay, so I'm going to set my color, because that's just what we want to look at, to be equal to my noise. Okay, so here we go. There's our alligator noise, but obviously it doesn't look the same as this noise, right? And that's because in here, this one is running with all these different parameters. Over here, we're running the simple version where we're just feeding it point position. Okay, so instead, let's move on to this mode where we actually have the turbulence, roughness, and attenuation included. Okay, so all I'm going to do, generally with a noise, you're going to want to do exactly this, as you want parameters exposed, because you want to just fiddle with the sliders and get the right kind of noise. Okay, so for the turbulence, it's an integer, right? Don't forget to look over here to see the type. So turbulence is always an integer. So I'm just going to call it turb. Then roughness is a float. Okay, and look here at the fact that the noise can be cast as a float or a vector, but no matter what it's cast as, the arguments are all the same. Okay, because even if you're creating three-dimensional, vector noise, your roughness is still a single value, and you cannot feed it a vector to get, a different roughness for each of the single components of that vector. If you wanted to do that, you'd actually have to run the A noise float version 3 times and compile that into a vector. Okay, So let's go channel float rough for roughness, and then attenuation as well. Okay, so there we go. There's parameters for the three controls that we want, and when I hit this button on the side here, then I get all my spare parameters. Now, in order to try and match this, let's set our values to exactly the same, right? So roughness is 0.5, attenuation is 1, turbulence is 5, I believe. Okay, yes, right. So if I switch back and forward now, yes, we do match, and we have exactly the same thing, okay? But here I have control over my frequency, my offset, and my amplitude. Okay, where is that in here? Okay, it used to match a second ago, but now it doesn't. So I have actually altered that noise, but there aren't controls for it. And if I look in the help file, okay, there is no control for amplitude, frequency, and offset. Okay, so remember, I started the last lesson showing you how you can alter the driver attribute to actually mimic, offset and frequency and amplitude. Okay, so this is exactly what we need to do here, because that's pretty much what's happening under the hood here anyway when it comes to this turbulent noise. Okay, is the frequency, offset, and amplitude are not actually being calculated as part of the noise, but rather they're alterations of the driver attribute, except for, okay, the amplitude is actually an alteration of the entire noise function. Right, so remember we showed that if we multiply our driver attribute, then we can control the frequency. So that's exactly what we're going to do here. We're going to multiply, and our frequency should match the type cast by the driver attribute. Okay, so if we're using point position, which is a vector, then your frequency ideally should be a vector. Okay, you can multiply a vector by a float, it will work. And if you specifically know that's what you want to do, then go for it. But my recommendation would generally be to multiply it by another vector. Even if that vector, you could link all of the components in that vector to be equal to the same, and then you're just changing the x, but your y and z will follow. It's just that when you realize that actually you want double the frequency on y, then you can just multiply by 2, and you've sorted that. Whereas if you fed this a float, then it's a lot more work to go and actually undo this, delete the parameter, and go and add a new vector parameter. Okay, so I'm just going to call it for frequency, and I'm going to run this, and obviously this is set to 0, so right now it all disappears. But if I set this to 1, it'll go back to what we had, or if I set it to what we have here, which is 4.4, then it should match. Okay, and like I said, if you want to, you could actually copy this and paste copied relative reference. So this is the equivalent of having it as multiplied by a float, but it gives you so much more control. You say, okay, well, actually, I want it now double the frequency on y, then you just do that, or you can take that away. You can break these at any time and make them whatever value you want. But in this case now, we can just control x, and it controls all axes exactly the same at the same time. Right, so we multiply to get our frequency. But now we need to add to get our offset, because you remember when we added to our point position, in other words, we're not, remember, just keep in mind, we're not altering point position, but we're taking the point position and adding another vector to it in order to calculate the sample location. Okay, so that's like me telling you to go outside and take a soil sample rather than doing it in your house. You're going to come back to that same location. You're not going to have altered your position, okay? But you're going to change your position, go and fetch some data, and then come back, okay? So when we add an offset here, where do we do it though? Because if we want frequency and offset, we need to be careful about where we place it. Okay. It would be possible we could just add, and then remember offset is also going to be a vector. Okay, same reasoning behind this. You know, you could add just a float, but then it's going to be the same value added on all the channels, and then sometimes that's not what you want. Okay, so we could add it here, or we could add it afterwards, right? But you'll see that when we go in here, and when I change the frequency, sorry, let's visualize this one. When I change the frequency of this noise, you'll see that it scales the noise around the center point. Okay, it scales inwards and outwards from the centroid. Okay, well, it'll scale around the actual world origin, and this is because it is multiplying the position before the offset is added. If offset is added before, if you know your basic maths, if this is added before, then when we multiply, not only are we multiplying the point position, but we're also multiplying the offset. So then as this increases, our offset would change as well. Okay, let's set our offset to be the same, 5.2. Okay, just so we can kind of get a similar result. Okay, and you'll see as we scale this up, it's not scaling around the origin. Okay, that's because we have an offset here. Obviously, if the offset was set to 0, then it would look the same. It would scale around the origin. And oh, actually, no, it won't. Look, it's because it's multiplying by 0. Okay, so what we need to do, take this. Okay, because you see here, the reason it's multiplying by 0 is because it's taking, I don't know if you guys call it anything different, but we call it a BODMAS, like, you know, it does brackets and then of, and then divide, multiplication, addition, and then subtraction. So it's prioritizing this multiplication function, multiplying by 0, and then adding it so nothing's happening. Okay. Basically, the best way to do this is to add after the fact. Okay, now if you wanted to be more pedantic and like kind of maybe even just visually clearer, you could actually encompass this in brackets to make sure that this is happening first, that this multiplication is happening first. But like I said to you, it will do the BODMAS, so your multiplication is going to happen before addition. Okay, but yeah, sometimes I like to just encompass it in brackets just to be pedantic and make sure that I remember, okay, I need to multiply first and then add the offset afterwards. Okay, if we do it this way, then when our values are the same here, then we will have the same result. Okay. Interesting that it's not the same. If we take this away, let's see if that changes. No. Okay. Well, let's continue and let's see if we can get it to look exactly the same. I mean, it looks similar, you know, it is the same kind of noise, but it's just interesting that it's got a different offset. Anyway, so now we're going to talk about amplitude, right? So that's something that we didn't even really specify last time. We just controlled the amplitude over here and got a certain result. You know, you can just multiply the entire values up and down. Okay, now this is quite a simple one. We are calculating this noise and we're getting a certain result, so we can just multiply that entire result by a float, by a number. And you know, because if we multiply it by 0, it's going to be 0, and it's exactly what's happening here with the amplitude. If we go 0, then it's going to come out 0. Okay, so all we're doing here to calculate amplitude is we're just multiplying at the end here by amplitude. Okay, and okay, let's put this to 1 so you can see, right? Now this here, the amplitude is a float. Okay, And I want to show you, I want you to be very careful and very specific about what you're casting. I told you here that with our driver attribute being a vector, you really want your frequency and your offset to both be vectors as well. Okay. These obviously all stay the same, but then this here, your amplitude, you kind of want it to be the same as the type of the noise, right? So if we wanted to, let's say we take, okay, well, let me change this to, if we wanted to actually create vector noise, okay, so actual color noise, and I change this to vector, technically what we should be seeing here is actually like a multicolored noise. But the reason that's not happening is because although we're casting to a vector here after the fact, our noise is being multiplied by a float. So when it multiplies by a float, it's kind of automatically casting itself. It essentially creates float noise instead of vector noise in order to multiply by this. So we would have to then also typecast this, or the best way to actually do it is to actually change your amplitude to a vector, okay? But then obviously we have to, well, okay, you can either come in and change it over here and actually change amplitude to a vector, but then again you're sitting with, you know, X, Y, and Z, which may be what you want. Or if you do want just a single amplitude slider, then instead of casting it here as a vector, you have the channel as a float, and then you cast it like this as a vector. So this will give you the correct result, but obviously this gives you less control. If you wanted a separate amplitude for each of your components, then you'd have to actually write this as a vector, delete this parameter and recreate it so that it's a vector, or just go in and change this to a float vector. Okay, so here we're multiplying, and you'll see there if I do this, so we're multiplying all the channels down from 1 to 0, okay, and we get three-dimensional vector noise. Okay, just want to see why this is still baffled as to why this is not the same. Anyway, doesn't matter. Right, so be very careful how we cast all of this. Cast your noise to the right type. Make sure you know what type you're using, okay? Make sure you know what type your driver attribute is, and therefore what your frequency and offset should be. And remember that they form your driver attribute in combination. So the original base multiplied by your frequency and add your offset, okay? Then your turbulence, roughness, and attenuation are all static, so turbulence is an integer, roughness and attenuation are floats, and then multiply by your amplitude, but again, be careful of the type, right? And the type that's being received. So here, if we were feeding this into a, let's say we did have vector noise, and we were feeding it into a float, you can select the channel of the noise. So let's say we wanted just to create a foo, then you would do noise dot y maybe to grab the y value of that noise. So then if I visualize foo, then you can see it, all right? And then if I grab x, then it'll be different. Okay, all right. So this is basically how to create noise. I mean, this is specifically on a noise, but you could just change it for S noise. Okay, in this particular case, S noise happens to have the same arguments as A noise. For some of the other noises, you will need to obviously change the actual parameters. So something like your V noise or Voronoi noise has totally different arguments. But again, something like your position, okay, is going to be, you're going to actually be able to multiply or add to it, the same as with your jitter, okay? So obviously read the help file to see what each noise requires of you, but just keep in mind that there are certain parameters that are actually available in a VOP that don't seem to be included in the help file arguments, because when you're writing it out, you actually have to control the offset and the frequency and the amplitude on the outside, right? And it's a little bit frustrating that this is not actually explained in a help file, because they're kind of operating under the assumption that everybody knows this, okay? But now you guys know it, so you can create noise in Vex. Hopefully you won't have to do this very often, because look, it becomes a real pain. Okay, creating one is not too bad. I mean, okay, it's a real mouthful of a line to type and a ton of parameters, but one is not too bad. Okay, but what starts getting a mess is when it's then, okay, but then I want to have another noise that I multiply it by as well. So noise 2, and then I want to noise, and then I start typing it. And then now I have multiple frequencies and multiple offsets, and I have to keep track of them in here and figure out which one is for which. It's a pain. But unfortunately, sometimes, on very rare occasions, I've had to actually create like 3 or 4 different noises within a Vex function. So at least you know how to do it now. Okay. So this concludes our lesson on noise. And I hope you guys enjoyed. I hope it makes sense and that you at least know how to use it and understand noise a little bit better, because it is a very, very powerful technique. And we'll see you guys in the next lesson.